Very grateful to Trinity College here in Cambridge, who have given us funding so that these events are free to you. We will be asking you for a bit of feedback towards the end of the session. Throughout this afternoon, we're going to be inviting you to participate using the chat. So do please contribute your thoughts where you feel able. And I really would like to emphasize that you should. Have I been on mute the whole time? Okay, I suddenly realized I was on mute.
Not the whole time.
You were on mute for just 2 seconds, Liz.
Okay, that's good. Suddenly I realized I was on. That's good. I just want to emphasize that you shouldn't feel like your thoughts have to be completely polished in order to contribute them to the chat. We really welcome emerging ideas. The intention this afternoon is that we're going to introduce you to our most recent feature, a group of tasks. We're going to have a go at them together here and now, and we'll think about how they might provoke mathematical thinking in your classrooms. So without further ado, I'm going to share the NRICH website with you. Hopefully you can see that. Charlie or Ems, would you mind confirming that you can see the NRICH yes. Site? Wonderful. So this is the homepage of NRICH, enrich.maths.org. And as we are here with you as primary practitioners, I would suggest that the best place for you to get used to going to on NRICH is the primary teacher homepage. And the easiest way to do that is using this button at the top in the menu bar there, because that menu is always on NRICH. So, as I say, we're going to concentrate today on our current feature, and the link to that is in this blue box. So if I click, this takes you to the feature page. If I just scroll down briefly, you get a little sense of what it contains. Throughout this session, Charlie and I are going to do a little bit of a double act and have a bit of a chat about the resources. Charlie is the secondary coordinator here at NRICH, whereas I'm the primary coordinator. So Charlie just doesn't know many of the resources quite as well as I do. But together, we hope that we'll illustrate how you could use them with your learners in the classroom. So Charlie, shall I kick off with a little bit of an overview of the feature?
Yes, please.
Okie doke. So as you can see, the title of our feature is Proof Through Words. Now, I think possibly when we hear the word proof as primary practitioners, we might feel a little bit intimidated. We might get that impression that proof is only for much older students with more mathematical experience. We might think that proof equals algebra, but we would really like to reassure you that that is not the case. What we've done here is we've gathered together a range of tasks which we hope will illustrate that primary children can prove. And we're going to do that by through a mixture of proof through words and words accompanying diagrams. Or diagram sounds very formal, pictures is a better word. Ems, who you met on just now, Ems has kindly contributed an article to this feature, which I would really urge you to read. And it talks about sort of 3 essential features of proof and how that can translate very easily in the primary classroom. I'm not going to go into any more detail now, but please do take a look at that later. Charlie, have you got any questions generally about the feature before we have a look at a task?
No, I was just thinking that if proof seems a slightly scary word because it's often associated with algebra, and it needn't, and I think we're going to make that point today. It's just as good to be thinking about justification and coming up with convincing arguments, and that is, in some cases, it isn't the equivalent of proof, but it's a really good preparation for what students will be expected to do at secondary level, where their convincing arguments and their justifications become a little bit more rigorous.
Absolutely. Thanks, Charlie. That's really helpful. So if I scroll down here, you can see that, as I said, that's an article. And then the other items that you can see here in the feature are different tasks for us to have a look at. Now, I hope you can appreciate, we're not going to have time, I'm afraid, to look at all these in detail, but we've picked out a selection to have a go at this afternoon. The Key Stage 1 tasks that we've got in this feature, and by Key Stage 1, I mean sort of aimed roughly at age 5 to 7-year-olds, are all relatively similar in their style. So the one that I'd like to share with you is this one here, 2 numbers under the microscope. However, I'm not going to actually click on it because I'm going to verbally take you through a little bit of it, and then we'll look at the actual task in a minute. So what I would like you to do, please, is choose 2 odd numbers and add them together. And if you could post your results in the chat, that would be fantastic. You may like to post the 2 numbers you chose as well. So please contribute your 2 odd numbers and their total. Brilliant. Thank you to those of you already on it. Now, I appreciate it's a bit difficult because they're coming in thick and fast. But I'm deliberately pausing to wait for some of you to contribute. Brilliant. So what do you notice about the results we've got? Have a little look. You can scroll using the little scrolly thing on your chat window, should you wish to look back. Some of you are straight in there with a suggestion. Okay. Brilliant. So at this point, if I was working with children and we'd done this in the classroom, what we might do is we might be collating some ideas on the board. We might be collecting up on the board the numbers that they've used and their totals. As we go, we'd probably be doing a little bit of a check of the arithmetic, just in case. Now, the vast majority of you, in fact, possibly all of you, have suggested that you've noticed that all of our totals are even numbers. Now, of course, in the classroom, children will say other things as well. And I guess it's important as practitioners that we do value what they say, even if we've got something in our mind that we're going to focus on subsequently. Now, you've made my life very easy because you've spotted that we've got even totals, and that's exactly what we're going to focus on. But just bear in mind, it might not happen quite like that in the classroom.
I was going to say that they're all less than 100, Liz.
Very good, Charlie. Exactly. And which is absolutely correct and well spotted. Thank you. So thinking about this idea, you have noticed that we've taken 2 odd numbers and we've added them together, and it appears that we always get an even number. My challenge to you now is to just take a few minutes. Can you think about how you would create a picture, or possibly a model if you had some sort of practical resources, a picture or a model that shows why your 2 odd numbers add together to make an even number. Have a think about that, and in a minute we'll look at some possible pictures, images that you might have done, and you may have come up with your own. So a few moments to think about that. A picture or a model that shows why your 2 odd numbers make an even number. Thank you to those of you who are contributing in the chat. I appreciate that it's not necessarily straightforward to explain what you're thinking if I'm asking you to create an image. Some of you are mentioning Numicon. Some of you, I like this suggestion from Julia, pairing the numbers using dots or counters. That's interesting. You could model with people, absolutely, with children, Saskia. So at this point, what I'd like to do is show you, is actually go to the task on the NRICH site and show you some examples of what children might do. And we'll have a think about each one. So here we go. This one's called Two Numbers Under the Microscope. There, the text at the top is just giving you an illustration. So the particular odd numbers which these children were focusing on were the numbers 5 and 9. And they were given the challenge that I asked you, how could you show these numbers being added together? So Adam found 2 dominoes, one with 5 spots and one with 9 spots. Sarai, by contrast, found some interlocking cubes, some multi-link cubes, and she's made there 1 blue block of 5 and 1 black block of 9. Abdul has drawn a picture, if you like. He's used squared paper so that each square is representing 1, and he's configured his numbers in a slightly different way. And this reminds me certainly of Numicon, which many of you have mentioned. So if we're thinking about these 3 images, I think that perhaps we could create a narrative using the second and third images, certainly. The first image, although it represents 5 and 9, I'm not sure that it helps us understand why those 2 numbers added together make an even number, although perhaps you would like to argue differently. Perhaps you can see something there which might help us. I'd like you to take a minute to choose one of these images and see if you could rehearse what it is about that image that helps us really understand why those 2 odd numbers added together make an even number. I'm going to give you a few minutes to have a think about that, and then I think Charlie and I might have a bit of a conversation to model what that might look like. But obviously, do please post your suggestions in the chat too. Of course, I can repeat the question. Yes. What I'm asking you to do is choose one of those images. If you have time, please do look at all 3 and consider what you might want to be saying. What kind of narrative, what would you want to say to accompany this picture to show that let me rephrase that. What would you want to be saying in order to convince somebody else that this does show that 5 and 9 adds together to make an even number? What is it about that picture that helps to convince us that that is going to be even? Thank you to those of you who've contributed so far. Thank you. Charlie, should we have a little bit of a chat about this together? A couple of people, I see some things, this idea of a lonely number or a lonely one is an interesting one. A couple of people have mentioned the idea of pairing and the odd one. Which image would you like to start with, Charlie? Which should we look at first?
I suppose the bottom one is the one that I associate most readily with two odd numbers being added together, because I see them as even numbers plus one.
Okay, so although in this particular example, what we've got here is 5 and 9, so we've got very particular examples. It's interesting what you say about even plus one. I'm just going to alter what I'm sharing with you. I'm going to try instead to show you some cubes, which I've got here. I'm hoping, can you see a line of orange cubes?
Yes.
Great. Okay, so Charlie, you said even plus one. So if here is here's a stick of orange cubes. So if I was going to try and find out whether this was an even number of cubes, I guess what should I sort of try roughly breaking it near the middle?
Yes, and if you can share them out evenly.
Right. So I've now got, I've managed to, effectively I've got pairs here. So exactly as you say, Charlie, that can be, the total number can be shared out evenly. I've got two identical columns. So here I've got an even number.
And I don't need to count, and I mean, I can tell very easily that there are 10 cubes, but I wouldn't need to know that there are 10 cubes to still be convinced that there are an even number of cubes. So
right. That's an interesting point, isn't it? We don't need to know exactly what the number is, but we can convince ourselves they're even. Okay, so by contrast, let's have a little think. What about, so here we've got a new number of cubes. Let me make sure you can see that properly. Should we try a different thing? Try the same thing in terms of I'll try and split it roughly in the middle. So what happens if we, okay, whoops. I'm trying not to pick them up so you can still see them. There we go. And this time, Charlie, we've got pairs, but we've got this extra one, which you were referring to earlier. So an even number plus one. Yeah? Yes,
so I sort of know that in the number system, it goes, if I start at 1, it goes odd, even, odd, even, odd, even, odd, even. So an odd number must be one more than an even number. So I can tell that this, again, without having to count the cubes, must be an odd number of cubes.
Right, great, okay. So why don't we take this odd one, if you like, and replace it with a yellow to make it really obvious. So here's another number, this time in green. So I'm going to do a similar thing. I'm going to roughly break it in half, pop it together. Let's have a little look. Can I make these connect together? There we go. Okay, and again, therefore, without knowing exactly what the number is necessarily, we can see that that is also an odd number. Let's replace this odd one at the top with a yellow. And so what that picture in the task, that third picture in the task is showing us is it's a drawing, if you like, of this idea. So that now these two odd numbers, I can see that if I push them together, those two yellow bits, the two odd ones, are going to pair up. And so I'm going to get an even number. Now, the interesting point, Charlie, is in the problem, we looked at the numbers 5 and 9. We haven't even bothered counting what these are. Let's do that quickly. This happens to be 9. Here we've got 7. But I think the really powerful thing about this model is that it can help us explain why any two odd numbers make an even number. Although we've got particular examples, that is the power to me. exactly as you've said, Charlie, if you've got an odd number, you've got the odd one that we've highlighted in yellow, the odd from each number will always fit together to make the pair, no matter how long these were, how big the odd numbers were. That's always going to be the case. Charlie, would you like to say anything else?
It can also convince me that if you had 3 odd numbers, I'd end up with sort of 3 yellow cubes, so I wouldn't have an even total. But if I had 4 odd numbers, I'd be able to pair 2 and then another 2. And if I had 5 odd numbers, it'd be, and I can generalize and I could think, oh yes, if I had 100 odd numbers, I could pair 50 with another 50, you know, I'd have 50 pairs.
Absolutely. Really powerful, a really powerful image. Now, from what you're saying in the chat, I can tell that many of you are very familiar with this kind of image for odd and even numbers, which is fantastic. And I think we can't underestimate how powerful that is for children. So what you have here, this is what I was getting at when I said that this is about proof using words and images in this case. We've got a very powerful image, and by talking through what the image is showing, we can effectively prove that 2 odd numbers added together make an even, and we can go further than that in exactly the way that Charlie describes. I'm going to stop sharing my cubes and go back to the problem. Oh no, not that one. Where's the enrich site? There, that one. Sorry, that took me longer than I was hoping. I'm hoping now you can see the problem again. So Charlie, you picked the 3rd image to go for straight away because that was the image that you immediately recognized. What about this 2nd image very quickly? Is there something, at first glance, it looks perhaps like it's not so helpful, but is there a narrative we can put on this one?
Yes, I think so. I mean, obviously, the blue cubes and the black cubes that are right below them must add up to an even total. But we also know the difference between odd numbers is an even number. So if I started any odd number and I add 2 or 4 or 6 or 8 or 10 or 126, 100, I'm going to get another odd number. So I know that the bits of black, without having to count the number of black cubes that go beyond the blue, I know that's an even number of black cubes. And so I'm going to be, I can, if I wanted to, break them up and share them evenly. So the blue cubes and the black cubes which are below can be shared out evenly, and the extra, the difference, can also be shared out. So that will also make an even total.
Really nice, thank you. And I really like that, because at first, as I say, at first glance it's perhaps not obvious, but for some children that might be a very accessible way of thinking about it. And I think I noticed a post earlier that somebody commented on that even difference, so thank you. Just very quickly before we move on to have another think about another task, the domino images I kind of dismissed as assuming that they weren't so powerful. They don't have that that sort of what I would call a generic idea that to demonstrate why 2 odds make an even. Now, I haven't seen any posts that have suggested differently, but if you think of something that you think could be useful, then do let us know.
Actually, somebody did.
Oh, sorry. Thanks,
well,
Charlie.
I mean, if you think about splitting an odd number, we've been thinking about splitting it into an even number plus 1.
Yes.
But you could also think about it as splitting it into an even number plus 3.
Oh.
So here you've got a 2 plus 3 and a 6 plus 3. So the 2 even numbers add up to an even total, and then you've got 2 identical odd numbers. So that will also add up to an even. So there will,
yeah, nice.
A suggestion that
nice.
That could be done.
Thank you. Great. Thank you to whoever suggested that. And I apologise that I didn't see that myself. So this particular task, obviously, you could use. You can encourage children to draw their own pictures. You can use Numicon. You can use, and I would urge you, if possible, to hold back from suggesting representations to your children and let them decide how they would like to represent this at first. It's hard to do. Even when you see them reach for something that you think is not necessarily helpful, like my assumption with the dominoes, try and hold back and listen to what they say. This task is what we would call a live task at the moment, which means that we are inviting children to send their solutions to us. So the deadline is the 31st of January. So if you do have a go at this task with your class, please do submit their solution. You could submit a whole class idea. We particularly look out for well-explained, well-reasoned solutions, not just answers. Charlie, is there anything you'd like to add about 2 numbers under the microscope?
Can you just show on the feature page how teachers can find out which are live and open for solution?
Good idea. So here we're back at the features page. So each of the tasks which has got a little grey live button next to them are those which are open for solution. And the others already have solutions accompanying them.
And if you click on them on the left-hand side in the menu, you get a link to submit a solution, don't you? That's
right. That's right. You could upload image files. You can put in text, link to other media. Okay, what I'm keen to do now, Charlie, is have a look at another task which follows on quite nicely. And this task is for slightly older children. Charlie and I have composed this task together to some extent because we think it really nicely bridges the Key Stage 2-3 gap. So I think I'm not going to click on the task again yet. I'm going to invite you, please, to this time think of 3 consecutive numbers and add them together. And please, in a similar way, could you post your numbers and the total that you have got? Do try it more than once, should you wish. So 3 consecutive numbers, and what is their sum? Thank you for all the suggestions pouring in. I'm sure you can guess what my next question is going to be. What do you notice about the totals of these of 3 consecutive numbers? What do you notice about the totals that people have posted? Lovely. This time we've got a little bit more variety. Some of your noticings, we're not necessarily all saying the same thing. Some of you are having a think about the nature of the total. Do we get an even total? Do we get an odd total? Somebody has posted how that differs depending on the 3 consecutive numbers you've chosen. Many of you have suggested that you always get a multiple of 3. And some of you are, oh, I like that. Mariam says, wow, how nice, Mariam, that you said, wow. That moment of surprise is really special, isn't it? Some of you have suggested, like Mariam, that actually the sum is 3 times the middle number. Okay, and exactly the same way as with our previous task, I would be collating all this on the board with children and encouraging them to offer their noticings, and we'd talk briefly about each one. For the purposes of here and now, let's focus on your noticing that it seems to be, from the examples that we've got, that when we add 3 consecutive numbers, we get a multiple of 3. So what I'd like you to consider is how, will that always happen? how would you convince somebody else that that is always the case? In a similar way, we'll look at some possible ways of doing that. But before we have a little look, I'd like you to have a think yourself. How would you convince yourself, convince somebody else, that 3 consecutive numbers always add to make a multiple of 3? So a few minutes to have a think. Thank you for the ideas coming in. Just another minute to contribute your thoughts. Thank you. Sadaf, I hope I've pronounced your name correctly. Thank you for your post. I tried multiple examples and all gave me a multiple of 3. This is really important, that one of the first things we might do quite naturally, if we are looking at whether something is always true, is we could generate lots and lots and lots of examples. And each time we're checking, is that a multiple of 3? Is that a multiple of 3? And that's sort of what we might do in the classroom at the beginning, because we'd be collating on the board. So there'll be lots of examples of this. However, in mathematics, creating lots of examples is not quite enough. A mathematician wants to be convinced that something is true. And this is where our idea of proof comes in. We're trying to create that watertight chain of reasoning so that we can say beyond doubt that it will always be the case. We cannot possibly test every single example. So this is the power of mathematics in creating that justification and that proof. Shall we have a little look at our examples in the task, Charlie, or is there something that you'd like to chip in first?
Well, only just to say that when you had your multi-link and the odd numbers, we were emphasizing the structure of numbers to come up with convincing arguments that something was going to always happen. So it can be very tempting to say, well, what Tim Rowland has written about, and there is, we have his article on Enrich about using a generic example. So taking an example that, well, if this works, it's fairly convincing that it should always work. If we take, I don't know, 347, 348, and 349, and that works, well, that seems to be good. But the lovely thing about maths is that if we can explain what's happening, and some people have been explaining it already, then that produces an argument which seems to be more convincing in terms of understanding and ensuring that, sort of believing that this is always going to happen.
Yeah, thank you. Your point about the structure of number, I think, is a really good one. Thank you. Okay, let's have a little look at the task. So the beginning is just what we've already done, and in a sort of a similar way to the previous task, we are offering here 3 different ways of thinking about it. Now, from what you've posted, some of these are very similar to some of your posts, and you might have thought about something slightly differently, and that is fantastic. Just for the interests of the webinar, we're going to have a little look at these 3 examples in the problem, and of course in the classroom, if a child had created something like this, you'd be using their example perhaps rather than that on the website. So Charlie, shall we start with what's called Liz's method, my method, if you like?
Yes.
So here, so I drew a picture, and this picture looks rather like what some of you were describing in the chat. Have a little think. How does that picture help convince me that 3 consecutive numbers always add up to a multiple of 3? Just have a moment to think about it, and then I'll ask Charlie perhaps, and we'll have a look at what comes in on the chat. So remember, it's what is it about that picture that helps convince me that this is always going to be the case? I appreciate that there's potentially quite a lot of words to type into the chat, so do feel free to abbreviate and, you know, thank you to those of you giving it a go. Well, that's an interesting point, Anita, yeah. This is really nice. So that your contributions, I like the fact that each of you are contributing something relatively concise, but in a classroom situation, we'd be drawing all this together to create something more rigorous. So Charlie, can I pick on you? What do you think? How could this picture convince us that 3 consecutive numbers always add to a multiple of 3?
Okay, well, yes, if I want to tell a story, I'm assuming that each square is worth 1. So I can see on the left-hand side 3 columns, which I'm interpreting, which I think are representing 3 consecutive numbers, because the middle column is 1 larger than the one on the left, and the right-hand column is one larger than the one in the middle. And to capture the generality of 3 consecutive numbers, you seem to have put some dotted lines, some stilts at the bottom, which seem to suggest that you don't want me to count how many squares, that we don't know how far down these numbers go. So they could represent 6, 7, and 8, but they could represent 106, 107, and 108.
Exactly.
And then what you're suggesting, I think, or what Liz's method is suggesting, is that you take the top, or you take 1 away from the largest number and you give it to the smallest number, and then you end up with a diagram like the one on the right, where you have 3 identical columns, and that seems to suggest that you have that the total will be the sum of those 3, and adding 3 identical numbers will give us a multiple of 3. And you've also got the extra benefit that you can see that it's 3 times what was originally the middle number.
Absolutely. So this particular image nicely actually proves some other noticings from earlier, even though we asked about the multiple of 3 more generally. Thank you, Charlie. Brilliant. And thank you very much for those of you posting on the chat. Let's have a little look at Charlie's method. So Charlie starts with 3 consecutive numbers, 1, 2, and 3. they add up to 6. Let me just make this a little bit bigger, perhaps. There we go. He then adds 1 to each of them, which gives him the next 3 consecutive numbers. They add up to 9. And then he adds 1 to each of those numbers again, which gives 3, 4, 5, and they add up to 12. So how does this method help to convince us that 3 consecutive numbers always add up to a multiple of 3? I wonder. I'm just going to give you 30 seconds to think about that rather than post on the chat, because I'm aware of the time and I know we've got one other task we'd like to show you after this one. So Charlie, what is it about this method? How would you convince us? Talk us, give us the narrative about this method. How is this showing us that 3 consecutive numbers will always add to make a multiple of 3?
Well, I suppose at the heart of this is a realization that the difference between multiples of 3 are multiples of 3. So if I start at any multiple of 3 and then add either 3 or 6 or 9 or yes, so if I keep adding 3s to multiple of 3s, I'm going to keep getting multiples of 3. So if we think about your image that we had earlier,
yeah,
if I keep adding 3 blocks to the right hand image, I'm going to get another multiple of 3, and I can keep adding sets of 3. So if I start with the smallest possible set of 3 consecutive positive numbers, 1, 2, and 3, I can see that I get a multiple of 3. I get 6.
Yeah.
Okay. So then if I add 1 to each of those numbers, to the 1, to the 2, to the 3, I get the next set of 3 consecutive numbers. And because I've added 3 altogether, because I've added 1 and 1 and 1, then I'm bound to get another multiple of 3. And then if I keep adding 1 to each of the numbers, I will get another multiple of 3 and another multiple of 3 and another. And I can see that, oh, so if I ended up adding 100 to each number, then that would have been a total of 300 more than my original number.
Yeah. Thank you. Great. Absolutely. Absolutely. And that's one, I have to be honest and say, I hadn't thought about it in that way until relatively recently, until Charlie offered that. But that's lovely and very convincing, absolutely convincing. We have one more method which we've included because those of you who are Year 6 teachers who are beginning to introduce algebraic representation, and those of you who perhaps teach in middle schools or slightly older children as well, may find this method useful. Now, the nice thing about this is actually, well, no, before I say that, let me just give you a chance to have a little read. Is that big enough?
Yes.
Great. So here, hopefully, we've laid out the steps here in such a way that even if it is a long time since you did any algebra, you can follow those steps through. And we end up here with this idea of representing consecutive numbers by n and n plus 1, n plus 2 is something that children get very familiar with as they get older and have more experience of algebra. And then adding these 3 together, you can see that we've kept the numbers. That's n, the first number, n plus 1, the second number, n plus 2, the third number. And don't worry if your algebraic notation is a bit rusty. We can add this together and we can represent it as 3n plus 3. So how does this help convince us that it's always going to be a multiple of 3? So, well, I guess, Charlie, if we've got 3n, 3 of a number, and another 3, we've got 3 of a number, of course, is a multiple of 3. And then if we've got added a 3 on top of that, exactly how you were saying earlier, we know that multiples of 3 differ by multiples of 3, if you like. So if we've got a multiple of 3 added to a multiple of 3, we are always going to get a multiple of 3. Would you like to say it slightly more eloquently?
No, you said it perfectly. So I'm going to add something completely different.
Okay.
We have a colleague, Claire, who, instead of starting with n and then adding n plus 1 and n plus 2, she would put n in the middle. And so the number before would be n minus 1, and the number at the end would be n plus 1. And she would do this because then when she adds it, she has n minus 1, n, and n plus 1, and it gives you a lovely solution of 3n, which is obviously a multiple of 3.
Just somebody has just posted that in the chat. Thank you, Danny. Yeah.
But otherwise, you could do what Armand has suggested, which is to factorize 3n plus 3. But again, that feels much more what secondary age students do. But that again is another way of convincing yourself that you're ending up with a multiple of 3. But like you said, you want students to appreciate that multiples of 3 go up in 3s. So if you've already got a multiple of 3 and you add another 3, you must get another multiple of 3.
Exactly. What's rather nice as well is that if you compare this algebraic method to the very first pictorial method, actually they link rather nicely. And so this would be a lovely problem to introduce, this would be a lovely problem to help, older primary children, lower secondary children get to grips with algebra, because those two, the image and the algebra, are so nicely connected. Okay, I hope that you can see the value of a task like this. Oh, what I didn't say, which I should have done, is that if you scroll right down to the bottom of this task, we've left you with a few thoughts, which I think a few of you had already posted in the chat. What happens when you add 5 consecutive numbers? What happens when you add 7 consecutive numbers? We don't have time now, and I'm afraid. However, could you use one of those 3 methods to try and convince yourself what is always going to happen with 5 consecutive numbers? You could probably make a conjecture. The lovely thing about this task is not only are we considering the generality of 3 consecutive numbers, but we're also considering the generality of those methods to apply to an odd number of consecutive numbers. Now, for those of you interested, if you'd like to investigate an even number of consecutive numbers, there is a task in the secondary feature which will provide you with challenge on that front.
Yes, ideally, Liz, I would ask students to adapt all 3 proofs. For 5 consecutive numbers and 7 consecutive numbers.
Yes, sorry, did I say to choose one? Yes, you're right, Charlie. Yeah, absolutely. I think a point that I heard Charlie making yesterday is that sometimes we have a method, we have methods for all sorts of things which we're really comfortable with, and sometimes we don't challenge ourselves to thoroughly explore a method which we're not so comfortable with. So yes, there's certainly value in having a go at all 3. Thank you. So we are rapidly approaching the end of the webinar, but I would like to share with you one last task. And that is something that actually we have literally, it's hot off the press. That's the phrase that I'm looking for, hot off the press. Let's have a quick look. And I'm going to put Charlie on the spot and ask him to have a little go at this, because I think observing what Charlie's doing will save a lot of verbal explanation. Here we have what we've called a Mathdoku. The idea is to complete this grid. Each row and column must have exactly one of each of the numbers 1, 2, 3, and 4. You've got some little clues, and you've got what we call cages. These the sort of the group of squares that are drawn together by that dark black line. Charlie, I'm going to put you on the spot, and I'm going to ask you, do you think there are any cells here, or which cells might you fill, or which cell or cells?
Okay,
so we might be able to fill in first.
The top right one seems to be saying to me that a 2 needs to go in there.
You're absolutely right. So I can click on here, and I can either, I just scroll down a bit. I can select a 2 there. I can just use my keyboard as well if I prefer. Great, thank you, Charlie.
And then to the left of that, there are 2 cells that have got when multiplied together, give a multiple of 3. So it must be 1 and 3, but I don't know in which order.
Okay.
So I'm not going to fill those. But
no, keep that in mind. Mr. Briscoe is giving you a hint, Charlie. He says top right and bottom right.
Yes. Okay, I'll come to the bottom right in a second. But
okay.
Given that I could put 1 and 3 next to the 2, yeah, I must have to put the 4 at the far left.
Nice reasoning. Okay.
So then the other 2 numbers below the 4 must add up to 5, because all those 3 numbers add up to 9.
9, it's telling you here, yeah.
So I think I'm going to have to use a 2 and a 3, because if I use a 1, I'm not going to be able to get a 5. So I think below the 4, I'm going to have a 2 and a 3, but I don't know which order. But it means that I will have used the 2, the 3, and the 4. So at the bottom left, I'm going to have to use a 1.
Nice. So what just to pause you a second, Charlie, what I love about this task is that opportunity to do that chain, a relatively manageable dollop, if you like, of watertight reasoning. You can hear Charlie convincing himself and convincing us that this has to be a 1, this has to be a 4. And that's what we're offering you in this task. That opportunity for children to really put together those convincing arguments. Sorry, Charlie, I interrupted me.
No, I'm glad you did, because I was beginning to get stuck. But I've realized that sort of in the middle, you can see a column that's got 4 and divide.
This one here, yeah.
So I think that means that if you divide one number by another, you're going to get a 4.
Exactly.
So the only way I can do that is to have a 4 and a 1.
Exactly.
So if I've got a 4 and a 1 there,
yeah,
I can't have a 1 above that column.
Good point.
And so those 2 empty cells in the top row, which need a 1 and a 3, need to go 3 on the left and 1 on the right.
Lovely. Really nice. Oops. There we go. I was too impatient. Fantastic. So you've completed 1 row. Brilliant, Charlie. I'm going to pause you there. I hope by just listening to Charlie and watching there, you've got a bit of a sense about how our Mathdoku works. So the interactivity you saw me, you just click to choose a cell, and as I say, you can either select from the bottom or you can type in. You might have noticed that I can click to deselect. You might have noticed that there's a little button at the bottom here, show me a square I can solve. So if you're stuck, you can be given a clue as to a square which can be solved at that point. A little question mark appears. Now that one is relatively obvious because we're told it's a 4 anyway, but you might need a little hint, and you can always click on that extra hint as well. I've been quite kind to Charlie, really, because what I've done is I've given Charlie a relatively straightforward example to start with. If you'd like to challenge yourselves and your pupils, if you click on the purple cog here, you can go to our settings menu, and you can change the difficulty. And as you can see, at any one difficulty, we have a selection of 4 different grids that you can try. In case you don't have access to the interactivities, or you would prefer students to be working away from a computer if you don't have the resources, we do also have printable grids. Of course, you then don't get the clues, the hints, but I can imagine that even if you're working at a computer, many children might like to have something available to jot on as well. Anyway,
so presumably, Liz,
yeah,
it's always possible to fill one of the cells without confident that it's the right thing to do.
You're absolutely right, Charlie. These grids have been carefully created so that you can at any one point, you can always fill in a square beyond doubt.
Okay.
And the level of difficulty, the ones which are more difficult mean that you might have to rely on a little bit of a longer chain of reasoning, looking at different possibilities compared with this one. Yeah, absolutely.
It'd be quite a nice thing to do in pairs and get students to convince each other that something is right.
Exactly.
We used to share a common room with somebody who used to do crosswords, and part of the conversation that she used to have with a colleague was, oh, I can do 4 down or 7 across, and they wouldn't tell each other what it was. So I can imagine some students perhaps saying, oh, I think I know which 2 numbers go in 7+ there on the second row. And if we put the 4 at the bottom, then it would be obvious what, so they can tell their partner what it's possible to do without telling them which numbers.
Exactly. Thank you, Charlie. So I'm afraid we're rapidly running towards the end of our time together. We've shown you 2 quite what I might call meaty tasks, and then here in the Math Doku we've offered you something a little bit more game-like. But something like this Math Doku, I think, is really good preparation for those chains of reasoning, which eventually, as Charlie said, will lead up into rigorous proof. I'm going to go back now just with a little bit of admin, just to share the PowerPoint again, just to take you through a few bits in case you don't know about them already. Charlie, can you see my PowerPoint slide?
Yes.
Brilliant. Okay, so that's our Twitter handle @EnrichMaths. If you don't already follow us and you're on Twitter, please do, because you'll find out about our latest news and also future events. Alternatively, or in addition, you might like to sign up for our email newsletter if you don't already. We've looked at a very small selection of tasks on Enrich this afternoon, all linked to proof. If you do not know about it already, that is a link to our curriculum mapping document, which takes you to all things curriculum linked on primary Enrich. And when I say curriculum linked, I mean linked to the objectives in the mathematics curriculum for Key Stages 1 and 2 in England, but of course, very similar all over the world. What we've taken you through today is our feature about proof with words, but you can find all our past features via that link. And very early next week, we'll have posted the recording of this webinar on that page. And so, do feel free to share that with colleagues should you wish.
Liz, some people are asking whether all these links can be emailed to them. So presumably an email goes out to everybody who's signed up for.
An email goes out to everybody who signed up for today, and in that email you will get a link to the recording, the page of the recording, and on the recording page you will find a PDF of this slide, so you'll be able to access all the links that way. Yeah, thanks, Charlie. So we would love it, please, if you could take a few moments to give us your feedback. As I said, we're very grateful to Trinity College here in Cambridge for funding this, and we want to try and make sure these events are as good as they can be. So we do welcome your feedback. We have been super, well, I say we should thank EMS, has been super organised, and in fact, the booking link for the next primary teacher event, which will take place on the 2nd of March, is already available. So If you've enjoyed what we've done this afternoon, do please sign up for the next one. And what we'll be focusing on next time is more proof, but this time in a geometrical context. So we hope to see you there.
Liz,
Yeah.
I wonder, could you put the link to the evaluation form in the chat?
In the chat, I will.
Because
Good idea.
Ems was going to do it, but I don't think she can. I think she's had a power cut at home.
Oh dear, right, yeah. Let me do that. Yes, I can do that.
It's worth emphasising that we do really value getting the feedback, and our funders who support us providing all these free webinars also like being able to see what teachers have to say
Exactly.
about it all.
There is a link. I'm hoping it's a bit longer than the one on the PowerPoint slide, so I'm hoping that works. Please do shout if that doesn't, and I'll try again. Thank you all. That all remains for us to be said really is thank you very much for your participation, and we hope you've enjoyed the afternoon. Have a good rest of your afternoon stroke evening, and we hope to see you again at a future event. Thank you very much. Goodbye.
The link worked, Liz. I've just tried it.
Great. Good. Thank you. Goodbye.